Welcome to the class of medical physics. In the previous lecture, we have spherical mirrors. In today's lecture, we have spherical lenses. What are spherical lenses? Why do we need them? So, lens is a transparent medium made up of glass, but it has or one, one or two curved surfaces. The behavior of lenses, however, depends upon the degree of curvature of a lens. Lenses are of two types, concave and convex lens, like we have two types of spherical mirrors, concave and convex. Convex lens is uh, very much similar in its nature to as that of concave mirror. Likewise, concave lens is very much similar in properties to that of convex mirror. So first we have convex lens, which is very much being similar with the properties and characteristics of concave mirror. The surface of this lens has an external curve that looks like the surface of a glass ball. When light rays fall on the convex mirror of this lens, when light rays fall on the convex surface of this lens, they tend to converge from their path. When parallel rays fall on the convex surface of this lens, they tend to converge and meet at a single point, which becomes known as the focus of that lens. Again, the focus of the lens depend upon the diameter of the lens. Where your point of focus is locating, it depends upon the diameter of the lens. The focal length is the measurement of focal point and the center of the lens. The focal length is the distance or the measurement of the distance between the focal point and the center of the lens. The focal point is also known as the principal focus of a lens. The convex lens work on the phenomena of refraction of light. Because this is a glass medium, light is entering from air to the glass, the it working principle will be worked on the refraction of light, which is used to see things properly. Convex lenses are used in microscope, magnifying glasses, and eyeglasses. So one thing is clear, the convex lens is going to be enlarge the object size, and the an image will be enlarged. Next is concave lens and the picture of both convex and concave lens. So if you can see, the convex lens is curved outside, both sides are curved outside. So it is a positive lens because light rays, if parallel light rays are entering to the convex lens due to the law of refraction, they are going to be diverged from their path, and due to that divergence, uh, they due to their refraction property of glass medium, they are going to be converged at one point. However, in the case of concave lens, the coming parallel light rays are going to be refracted in glass medium, and due to its shape, it is going to be diverged in different directions, in all directions. Due to so the bottom line and the conclusion is that the formation or the shape of these glass medium, basically these two lenses, either the concave or convex lens, these two are nothing but a piece of a glass. So on what basis the light rays, the parallel beam of light rays, from in one scenario they are converging at one point, in another scenario they are diverging in different direction. So what is making them converging and diverging lenses? This is nothing but the formation of that glass material, right? So if you just have a rectangular glass piece material over here, you do have simple refraction of light. But in order to make them a convergent one and a divergent one, we do have certain pattern of that glass piece, that glass material, so that we can ensure the conversion of light, the conversion of light rays in one scenario, and the diversion of light rays in another scenario, because these two scenarios are beneficial for the formation of image in either enlarged form or in either diminished form. So that is why we do have convex and concave lenses. Other thing that convex lens is known as a positive lens because object is found at one side of the lens, and image is formed as at another side of the lens. Whereas in concave lens, what happens? The image and the object and the image both are found to be at the same side, and it is known as the negative lens. Another reason of its negativity or its positivity is the power or focal length of these two. As you can see, it has a focal length of 20 centimeter, and the power formula for power is 1 over focal length. So it is going to be 5 diopter positive, whereas the focal length is negative. Why do we have negative focal length in case of concave mirror? Because image is forming on the same side of the object where the object is present. That is why we do take focal length as negative. So 1 upon negative of the focal length will give you a negative of the power. So just see the properties of concave lens. Lenses are also called divergent lens. Which lens? The concave lens is also known as divergent lens, as the parallel beams, when incident on their surface, tends to diverge from their path. Concave lenses can never produce a real image because image is forming on the same side as the object, as their property is to diverge light rays away from their path. It means that the light rays will not converge and meet at a point physically. So we do have to uh, draw a virtual dotted lines on the same side of the lens where the object is present for image formation. That is why the image is not real. We are virtually forming the image. That is why it is known as a virtual image. When the rays are produced backward in a virtual way, they meet at a point and will form a virtual image. If you follow the equation of focal length and object distance, you will find the image distance always comes negative because the image will form at the same size where the object is present. It means that the image will form on the opposite side of the refracted rays. Why do we have negative answer? Because the refracted rays at are present on the, of course, other side of the object, but we have to redraw those refracted image on the opposite side. The lens strength in diopter is defined as the inverse of the focal length in meters. We have discussed just earlier that the power or the strength of a lens is measured in diopters, and it is inverse of the focal length when represented in meters. This is one image formation, image formed by a convex lens. This is your convex lens of certain diameter, which will describe its focal length. You have object at one side, the image is forming at the opposite side. The image is real because we have refracted ray for the image formation, a proper real-time refracted ray for the image formation. However, the image is inverted. Okay, image is inverted. Other terminologies are the object distance, the image distance. You can see the focal length and image are at the same side. And we have the lens formula as 1 over image distance minus 1 over object distance will give you the inverse of the focal length. Next is um, the different cases of convex lens for the image formation. For example, if your object is at infinity point from the convex lens, the rays coming from that object are supposed to be parallel. All the rays of light, all the beams of light coming to the lens from object which is present at infinity are supposed to be parallel with principal axis. So all those parallel rays of light from with principal axis are going to be converged at one point of focal length, and it is known as uh, a converging point of the mirror where image will form, right? Number two, in second case, object when object is placed and present beyond the center of curvature point or beyond the 2f, you can see the image is forming on the opposite side, on the other side of the lens between the focal point and the center of curvature. In the third case, when object is placed at the point of center of curvature and the light rays are passing, incident light rays are crossing the lens, the image will form on the other side of the lens at the point of center of curvature. So if the object is present at the center of curvature, the image will form by the convex lens on the opposite side of the lens exactly at the point of center of curvature. Next case, when object is present in between the focal point and center of curvature, the image will form behind the center of curvature. The image is enlarged. In the previous case, the image size was similar, image was of same size as that of object. But in this case, the image is enlarged. So whenever you want to enlarge any object, you just need to keep your lens at the distance with the object, which is in between the distance of focal length and center of curvature of the lens, right? So you just need to adjust your object placement with respect to the lens for enlarged image. Next is when object is placed at the point of focal point and when object is present between the pole and focal point. When object is present at focal point, the image is going to be formed somewhere away, far away, because the light rays, the ray diagram is showing the light rays are going to be parallel, and the parallel lines are will never meet with each other. So the image you can observe by this scenario will be blurry or so much unclear. In the last case, when object is placed between the focal point and the pole, you have likewise scenario, but if you just the lines are not parallel, so but the light rays are the refracted light rays emerging from the lens are in diverging nature. So whenever you have a diverging lines, you just need to draw them in backward direction for a virtual image. So this is your virtual image through dotted lines at the same side of the object, and the image is enlarged but the image is virtual and upright. So here are all 6 scenarios for image formation by a convex lens. Next picture is defining you array diagram of concave lens. Concave lens, you can see the object is present between the focal point and center of curvature. The light rays incidenting on concave lens is going to be diverged, the blue one and the green one. So you need to mm, all of them. So you need to draw them in backward direction, which will form an image in a virtual form in upright scenario, but in diminished size. Next is 2 scenarios and cases of convex and concave lens. Where do we need them in our real life? In the form of far-sightedness and nearsightedness, we have their applications. Far-sightedness is the result of visual image when image is being focused behind the retina rather than directly onto it. Okay, we all know that if you see any object, the image of that object is formed at the point of retina of your eye, the back side of the eye. But if in case of far-sighted people, what happened? They can see the far objects clearly. A far-sighted person sees far away objects clearly, while objects that are near are blurred. As you can see in this picture, this is a representation of a far-sighted person, the person can see a place far distant object clearly because the image is forming exactly at the point of retina. However, if the object is present very much closer to the eye, the image is forming somewhere behind the retina. So the person can only find a blur image of that object, but not a clear one. But due to the presence of convex lens in between the convex lens of human eye and the object, you can relocate that behind image exactly on the retina. So, because the light rays are being converged at the point of retina due to convex lens. On the contrary, a nearsighted person can see a near object clearly, but he cannot see a distant object clearly, but in blurred form. So, nearsightedness results in blurred vision when the visual image is focused in front of the retina. In this case, far objects will form just before the retina rather than on exactly at the point of retina. This could be this could be cured with the presence of concave lens between the eyeball and the object. Due to that, the image will be diverged and going to be formed at the point of retina uh, due to the presence of this concave lens. So these were two applications of the real-time application of convex and concave lens uh, found in or used in far-sight and nearsighted persons. Hope this is clear up to you. See you in the next lecture. Thank you.